Welcome back, class. Today we're going to finish Chapter 1 by talking about this particular way to define functions that we're going to use a lot in the next chapter. Okay. Namely, these functions are called piecewise functions, and you'll usually see them written something like this. And you've probably seen something like this before. And so what's really happened here is that we've basically sort of smooshed together three different functions. So we've put together the function 2x plus 1, the function x over x squared plus 1, and the function x squared minus 4. And the way we sort of mooshed together these three functions is based on what the input is. So these conditions, which row depends on the input. And so, for example, if you go to calculate f of 8, I have the input here 8. And I look here, 8's not less than 0, 8's not between 0 and 3, 8 is bigger than 3, so that means I use the function here in the last line. Again, this condition is what tells me that when I'm evaluating this function at 8, I need to use this third line. And so this is 8 squared minus 4, and so it is 60. If I took f of minus 3, here the input again is minus 3. And I look, and actually minus 3 is less than 0, so that means I use the first line. And so this is 2 times minus 3 plus 1, which happens to be minus 5. Now, there's the sticky question of what do you do if you put something like f of 0? 0 is sort of right on the border between the first line and the second line. But actually, we can see by comparing this piece and this piece that 0 is really supposed to go into the middle line, because here it is 0 less than or equal to x, and here it is x less than 0. So the strict less than means 0 is not included, whereas the less than or equal means 0 is included. So I use the second line, and I would get 0 over 0 squared plus 1, which is just 0. Now I want to emphasize piecewise functions are still in particular functions, and so that means every input can only have one output. So even though there are these three options for which that output might be, only one of them can occur at a time. And again, these conditions here describe the times. Now, I'll note, because this is a function, and we just evaluated the function at 0, that told us the y-intercept. So the y-intercept of this function is 0, 0. And so that tells me, in fact, that 0 is also an x-intercept. Let's try and decide if we think there are any other x-intercepts. And so how are we going to do that? We're going to look at each piece of this function separately. So I'm going to call these pieces 1, 2, and 3. And I'm going to copy here onto the next sheet. Piece 1, that was 2x plus 1. Piece 2, that was x over x squared plus 1. And piece 3, that was x squared minus 4. And I want to find out the x-intercepts. That is, I want to know when these things are 0. That is when the output is 0. So I'm going to do this piece by piece. So when is 2x plus 1 equal to 0? Well, 2x plus 1 equals 0, 2x equals minus 1, x is minus a half. When is x over x squared plus 1 equal to 0? Well, this is a fraction, so I only have to look here at the numerator, and so this piece is 0 when x is 0. And when is x squared minus 4 0? Well, x squared is 4, which means when x is plus 2, and when x is minus 2. Again, don't forget when you have x squared equals something, you're going to get two solutions, a positive one and a negative one. Okay. And so at first, when you look at this, you might think, great, we've got 4 different solutions. They'll all work out, and then we'll have 4 x-intercepts. But it does not work that way. Okay, and so not all of these are x-intercepts. And so here we have to figure out why. What's going on? One way to figure out why, or one way to figure out which ones actually do correspond to x-intercepts, is to go ahead and plug each of these things into my original function. Okay. So if I did plug in this minus a half, I'll get f of minus a half. I'll look here and say, okay, minus a half is less than 0. So I will get 2 times minus a half plus 1, minus 1 plus 1, that is 0. Okay, so that tells me this is a real solution. It really does give me something where when I plug that in, I get an output of 0. So that's telling me that minus 1/2, 0 is really an input-output pair, and this point is on the x-axis, so this is an x-intercept. All good. We actually already checked that f of 0 is 0. And so that tells me that 0, 0. That's a real input-output pair. That's an x-intercept. So I've got 2 more to check. What happens if I plug plus 2 into f? If I plug plus 2 into f, 2 is between 0 and 3, so it goes into the middle line, and I get 2 over 5. But that is not 0. So although these two both give me legitimate, honest x-intercepts, this does not give me an x-intercept. And if I plug in minus 2, where does the minus 2 take me? Minus 2 is less than 0, so I plug this into the first line, and that first line gives me minus 3, which is also not 0. So this also is a fake solution. So you might ask, how did this happen? How did we get 2 correct solutions and 2 fake solutions? And we can actually solve that mystery by looking at what we did to find this plus 2 and minus 2. Namely, this plus 2 and minus 2 are the things that make x squared minus 4 0. They're the things that make this piece of the original function 0. Okay. And so if I plug 2 or minus 2 into x squared minus 4, I really do get 0. However, the rules of the function do not allow me to plug plus 2 or minus 2 into this piece, because both 2 and minus 2 end up not in this piece of the function, but in the first piece and the second piece. Okay. So when I do this process, that is, when I find all of these zeros, what I'm really doing is finding potential x-intercepts, but then I have to go back and actually check, because the only ones that are going to work are going to be the ones where the corresponding input, for example, minus a half, actually lives in the line I was solving for. So in this case, I was solving for line 1 being 0. I found that that happened when x is minus a half, and minus a half really is less than 0. Hooray, I get a genuine x-intercept. For line 2, I solve for when that's 0. I get x equals 0. I look at this. 0 just inches in to the second line, so this is a real x-intercept. But then these, they do not end up in the third line, so no x-intercepts. Now, we can play all the same games with a piecewise function that we could with any of the other functions. So I could ask you, for this same piecewise function, what are all the points on the graph with x-coordinate 12 or y-coordinate 12? Remember, I am still talking about this same example. Okay, so let's first do x-coordinate 12. So that means the point looks like 12 comma something. And so in particular, when I'm looking for points where the x-coordinate is 12, I'm looking for the input to be 12. And so the matching output to go with that input is f of 12, which I can pull back my handy-dandy thing. 12 would live in the third line, and so I'm going to get 12 squared minus 4, which is 140. And this is my only point with x-coordinate 12. Again, I can't plug 12 into the first line or the second line because the rules of the piecewise function do not let me. 12 can only go into the third line here. What about y-coordinate 12? Well, now I'm looking for an output of 12. And so much like we did for the x-intercept, back in this example, I have to look piece by piece and find when each piece gives me 12. So piece 1, I need to know when 2x plus 1, that's the output here in the first line, I need to know when that is 12. So I'll solve that. So it'll give me 2x is 11. And that will give me x is 11 halves. And let's go ahead and see right now, do I believe this? Is this a real solution or not? Okay. And so what is this saying? This is saying if I plug 11 halves into this top line, then I get 12. Okay. So the question again is, do I get to plug 11 halves into this top line? And the answer is no, because 11 halves isn't less than 0. 11 halves, in fact, is more than 3, so it would go in that line. And so what that means is that this is a phantom solution. What about x over x squared plus 1 equals 12? When does this happen? Well, I need to multiply the x squared plus 1 over. So I'll get x is 12x squared plus 12. So I'll get 12x squared minus x plus 12 equals 0. Okay, I might try and factor this, but it doesn't look like it factors. So I suspect that this equation might actually have no solutions. How do I check that? Remember, I calculate the vertex. So what's the x-coordinate of the vertex? It's negative b over 2a, which is 1 over 24. Okay. And so my x-coordinate here is 1 over 24. What's my y-coordinate? It's what I get when I plug 1/24 in here. It would be 12 times 1/24 squared minus 1/24 plus 12. Now, this looks like a horrible mess, But the only thing I actually care about this horrible mess is that this mess is positive. Which is to say that the vertex of this parabola, if I were to draw it, and I'll make a little space up here, the vertex of this parabola lives in what we'd call the first quadrant. That is, the x and y coordinate are both positive. Okay. How do I know this is positive? Well, 12 divided by 24 squared is definitely positive, and 12 is positive. And then what have I subtracted from adding these two positive numbers? Minus 1/24th, which is much smaller than 12. So when I add these, I already get something positive, and then I add something positive to it. Okay. So that's where my vertex is. So which way does this parabola point? Well, it points up because of this 12. It's positive, so it points up. And so the graph looks something like this. And so, in particular, the graph doesn't hit the x-axis, so there are no x-intercepts for this piece. So there are no inputs where x over x squared plus 1 gives the output 12. Okay, then we have to handle the third line. So remember what the third line was. The third line was x squared minus 4. And we want to know when that could give an output of 12. Well, that's going to happen when x squared is 16. So that is when x is plus 4, or x is minus 4. Now take a moment. Does one of these work? Do both work? Or do neither work? Take a moment and think about it before I tell you. If you said one of them works, and the one that works is x is plus 4, you are correct. Because if x is plus 4, when I follow my rule, I find out that x equals plus 4 gets plugged into this line, because 4 is greater than or equal to 3, and that is exactly the thing we were solving for. 4 squared minus 4 is 12. Okay. Minus 4, though, that would get plugged into the first line. It does not get plugged into x squared minus 4, so this is not a real solution. And so, in particular, if we go back to the question we had asked, which was, what are all the points on this graph with y-coordinate 12? There were none of them in section 1, none of them in section 2, and then in section 3, we found just one, namely the one where x is 4. So there is exactly one point on this graph with y-coordinate 12, and it is 4, 12. And so that gives me my answer to my question of which points have x-coordinate 12 or y-coordinate 12. Okay, so that's one very thorough example of all the joyous things that we can do with piecewise functions. In the next video, I'll talk a bit about the graphs of piecewise functions. But that's all for now. I'll see you next time.